So question number 7 of February March 2022 paper 4 variant 2 says alternating current is converted into direct current using a full wave rectification circuit. Part of the diagram of the circuit is shown in figure 7.1. Part 1 says complete the circuit in figure 7.1 by adding the necessary components in the gaps. So we can clearly see that there are two diodes missing, and we need to add the diodes in the correct direction, and this here is the correct direction. Part 2 says on figure 7.1 mark with a plus the positive output terminal of the rectifier. Now let's see. So if this here is the positive terminal, at some point in time current flows from this point up till this junction. It goes through the top diode. At this point it can't go downwards, so it takes this path and down to the DC output. So the top part of the DC output is positive. When the current is in the other direction, so let's say this here is positive, just to double check whether we've got the diodes right or not. Current flows like this to the top. It can't take the bottom path, so it takes the top part, goes here and down at the DC output. So once again this here is the positive, so you either draw this red positive sign or the blue one. Part B of the question says the output voltage V of an AC power supply varies sinusoidally with time t as shown in figure 7.2. Determine the equation of V in terms of t, where V is in volts and t is in seconds. So the equation will be V is equals to V naught. The general equation is V is equals to V naught, because it's a sine graph, sine omega t. We've got the value for V naught, which is 3.5. We need to figure out the value for omega. Omega is 2 pi over the time period. So 2 pi over the time period, which is 2.5 seconds. This here is 2.5. And that gives us 0.8 pi. So V is equals to 3.5 sine 0.8 pi t. Part 2 says the supply is connected to a 12 ohm resistor. Calculate the mean power dissipated in the resistor. So the mean power can be calculated using the RMS value. So power is equal to V squared over R, but we'll be using the root mean square value of voltage. VRMS is V naught upon square root of 2, the entire thing squared, multiplied by 1 upon R. So this can be written as V naught squared over 2R. The value of V naught is 3.5 squared upon 2 times the resistance, which is 12 ohms, and that gives us the mean power, which is 0.51 watts. Question 8 says state the formula for the de Broglie wavelength lambda of a moving particle. State the meaning of any other symbol used. So the formula for de Broglie wavelength is lambda is equals to h over p, where h is the Planck's constant, and p is the momentum of the particle. Part B says electrons accelerate through a potential difference, pass through a thin crystal, and are then incident on a fluorescent screen. The pattern in figure 8.1 is observed on the fluorescent screen. State the name of the phenomenon shown by the electrons at the crystal. So what is this phenomena that we are seeing? We basically see rings of electrons. When those moving electrons pass through a crystal, this is basically diffraction. Just like diffraction of light when it passes through a diffraction grating. Part 2 says state what this phenomena shows about the nature of electrons. This tells us that even though we thought that electrons are just particles, in reality, moving electrons behave like waves. Part 3 says, suggest why the thin crystal causes the phenomena in B part 1. Now, when you talk about diffraction, you won't always get diffraction even when you have wave. When a wave passes through a slit, unless certain conditions are met, you won't experience diffraction. And those conditions for this electron is that the spacing between the atoms of the crystal should be approximately similar to the wavelength of electron. For waves, it's important that the wavelength of the wave is similar to the slit size or the slit opening. That is when you'll observe diffraction. Part 4 says, the electron is accelerated through a different potential difference. The new pattern on the screen is shown in figure 8.2. State and explain the change that has been made to the potential difference to create the pattern shown in figure 8.2. Now let's compare the pattern that we had earlier and the pattern that we have now. So this here was our original pattern. Let's have it right next to the new pattern. So this here was our original pattern. The new pattern, what has happened to the new pattern is that in case of the new pattern, the rings are closer together. For the older one, they were further apart. So in the new pattern, we can clearly see that the diffraction is lesser. And that has happened that will happen when the wavelength decreases. And how does the wavelength decrease? When the momentum increases, because the wavelength is inversely proportional to the momentum. So lambda, the wavelength has decreased, or I can say the momentum has increased. Now, how do you increase the momentum? You increase the momentum by increasing the velocity. To increase the velocity, we'll have to increase the potential difference that accelerates these electrons. So the potential difference was increased. Question 9 says, polonium-211 decays by alpha emission to form a stable isotope of lead. Complete the equation for this decay. So alpha is 4 nucleon number, 2 is the proton number. The equation should balance out. So this has to be 207, because 207 here plus 4 here gives you 211. And this should be 82. Part B says, the variation with time t of the number of unstable nuclei n in a sample of polonium is shown in figure 9.1. At time t is equal to 0, the sample contains only polonium-211. Use figure 9.1 to determine the decay constant lambda of polonium-211. Give a unit with your answer. We know that half-life T half is equals to ln2 over lambda. Now, polonium started off with 24 into 10 to the power 12. After one half-life, we'll be left with 12 into 10 to the power 12 number of unstable nuclei. And the time it takes for one half-life can be read from this graph. And this is equal to 0.52 seconds. So if we rearrange and make lambda the subject of our equation, lambda is equals to ln2 over t half, which is equals to 0.52 seconds. The answer that we get is 1.33, and the unit is per second. So lambda is equals to 1.3 unit per second. Part 2 of the question says use your answer in B1 to calculate the activity at time t is equals to 0 of the sample of polonium. Now, activity can be found using the formula A activity is equals to lambda times n, the number of undecayed nuclei. At time t is equals to 0, lambda was 1.3, lambda is 1.3. At time t is equals to 0, the number of undecayed nuclei that can be read from the graph, these are 24 into 10 to the power 12. So we'll simply use this value, 1.3 times 24 into 10 raised to the power 12, and this is equals to 3.1 into 10 raised to the power 13 becquerels. Part 3 says, on figure 9.1, sketch a line to show the variation with T of the number of lead nuclei in the sample. So polonium decays into lead. So as the number of undecayed nuclei of polonium decrease, the number of daughter nuclei of lead, they increase. And the sum should always be constant because polonium decays into lead. One polonium decays into one lead nuclei. So we'll start off with 0, 0. And after one half-life, we lose half of polonium, which is basically 12 into 10 to the power 12 particle. That would give us the same amount of lead nuclei. So our graph should pass through this point. At the end, at 1.2 seconds, we are left with 5.2 into 10 raised to the power 12 particles. So if you're left with 5.2 into 10 to the power 12 particles, and we started off with 24 into 10 raised to the power 12, that basically means we now have 18.8 into 10 raised to the power 12 particles of lead at a time t is equals to 1.2 seconds. So this is 18.8 into 10 raised to the power 12. So we should have a curve with a decreasing gradient, and it should pass through all of these points such that it will basically, the curve that we're drawing is basically a reflection of the original curve at this line. Moving on. Part 3 says each decay releases an alpha particle with energy 6,900 kilo electron volts. Calculate in joules the total amount of energy given to alpha particles that are emitted between t is equals to 0.3 and t is equals to t is equals to 0.9 second. So what is the count at t is equals to 0.3? At t is equals to 0.3, the count is 16 into 10 to the power 12 particles. At t is equals to 0.9, at this value, the count is 7.2 into 10 to the power 12. So how many nuclei of polonium decayed in this time period? We'll just subtract the two values. So 16 minus 7.2 into 10 raised to the power 12. This gives us 8.8 into 10 raised to the power 12 particle. Now each decay gives an energy equal to 6,900 kilo electron volts. These many particles would give 8.8 into 10 to the power 12 multiplied by 6,900. But they don't want the answer in kilo electron volts. They want the answer in joules. So kilo is basically 10 to the power 3. Electron has a charge of 1.6 into 10 raised to the power minus 19, and that gives us the answer in joule. It's simple multiplication. What value do we get? Let's see. . this is equal to 9.7152 or 9.7 joules. Part 2 says, suggest why the total amount of energy released by the decay process between time t is equal to 0.3 and time t is equal to 0.9 is greater than your answer in C1. Why is it that the actual energy is greater than the answer over here? Now what is this 9.7 joules? This is the energy possessed by the alpha particles. You need to understand, when the daughter nuclei are formed, which is basically a lead nuclei, they may have some kinetic energy, and that will also contribute to the total energy that we're ignoring right now. Similarly, we may also have gamma photons being emitted out, and that is also another source of energy. So that will add to our total energy. So our total energy would be greater than this value. So you may either write gamma photons are also emitted, or we may write that the lead or the daughter nuclei may have kinetic energy. Question 10 says, in an X-ray tube, electrons are accelerated through a potential difference of 75 kilovolts. The electrons then strike a tungsten target of effective mass 15 grams. The electron energy is converted into the energy of an X-ray photon X-ray photons with an efficiency of 5%. The rest of the energy is converted into thermal energy. So 95% of the kinetic energy of the electrons gets converted into thermal energy. The X-ray tube produces an image using a current of 0.4 ampere for a time of 20 milliseconds. The specific heat capacity of tungsten is 130 joules per kilogram per Kelvin. Determine the temperature rise delta T of the tungsten target. So I know that the accelerating voltage, which is V, causes an increase in kinetic energy, and that increase in kinetic energy can be calculated using VIT. Energy is equal to VIT. Now 95% of it gets converted into heat energy. So 0.95 gets converted into heat energy and causes a temperature rise, hence MC delta T. We've got the potential 75 into 10 to the power 3, 75 kilovolts. The current is 0.4 amps. The time is 20 milliseconds. Into 0.95, which is equals to M, the mass, which is 15 grams, convert that into kilograms, 15 to 10 to the power minus 3, times the specific heat capacity, 130 joules per kilogram per Kelvin. So whenever you get the value for specific heat capacity, always double check, because in some cases they'll give you the value as kilojoules per grams or kilojoules per kilograms or joules per gram. So you'll either have to convert the heat capacity into the appropriate unit, or mass into grams if needed, or energy, or some other change. So in this case, it's you don't need to do any conversion. Times delta T. We'll make delta T the subject of the equation, and that will give us the rise in temperature, which is equal to 290 Kelvin. Part B says the linear attenuation coefficient of the X-ray photons in muscle is 0.22 per centimeter. Calculate the thickness T of the muscle that will absorb 80% of the incident X-ray intensity. Now I is equals to I naught e to the power minus mu x. That is the formula. So let's say we start off with I naught. After 80% of it is absorbed, we'll be left with 0.2 I naught, or 20% of the initial value. The I naughts cancel out. E to the power minus mu, which is 0.22 times x, which is our unknown. adding ln to both sides of the equation, ln 0.2 is equals to minus 0.22 x times ln e, which is equals to 1. So it's not needed here. We'll make x the subject of our equation. X is equals to 7.3 centimeters. Because our linear attenuation coefficient was in per centimeters, our answer is in centimeters, so 7.3 centimeters. Part C of the question says, table 10.1 shows the linear attenuation coefficient mu for the X-ray photons in different tissues. So we've got the mu value for bone, blood, and muscle. Two X-ray images are taken, one of equal thickness of bone and muscle, and another of equal thickness of blood and muscle. Explain why one of these images has a good contrast but the other does not. Now, contrast basically depends on the amount of X-ray that is absorbed. So if two different tissues absorb the same amount of X-rays, the contrast wouldn't be good. If the two tissues absorb different amount of X-rays, the contrast would be good. And that the amount of X-ray that is absorbed depends on the linear attenuation coefficient. So we can clearly see that blood and muscle have roughly the same value for linear attenuation coefficient. So they'll both absorb the same amount of X-ray. So we'll get an equal amount of blackness on our X-ray film. So the contrast won't be good. Or we can see that bone and muscle has mu value that is far apart. They've got different mu values, very different mu values in fact. And that would result in a good contrast. So mu value of bone and blood is very different. So different amount of X-rays would be absorbed. And that would result in a good contrast. Positron emission tomography PET scanning obtains diagnostic information from a person. The information is used to form an image. PET scanning uses a tracer. Explain what is meant by a tracer. A tracer is a substance containing a radioactive nuclei that is introduced inside the patient's body. Or that is absorbed by the tissues. PET scanning involves annihilation. Explain what is meant by annihilation. Now, before we move on and answer this question, let me give you a brief overview of what happens in a PET scan. In case of a PET scan, a tracer that basically contains a radioactive nuclei, a biological molecule is used to inject that radioactive nuclei, that is a tracer, is injected inside our body. It's absorbed by the tissue that is being studied, and because it's radioactive, it decays. When it decays, it emits out a positron. That positron interacts with an electron and it annihilates. Annihilation is basically when a particle interacts with its antiparticle and mass of both converts into energy. That's what annihilation is. After that annihilation, we get two gamma photons that travel in opposite direction. They exit our body and they are detected by detectors outside. So back to the question, what is annihilation? It is when a particle interacts with its antiparticle and their mass gets converted into energy. Gets converted into energy. State the name of the particles involved in the annihilation process. So the particles that are involved, as we discussed just now, is a positron and an electron. Calculate the total energy released in one annihilation event. What is the total energy release? Now, energy that we get is from the mass of these particles. E is equals to mc squared. Now the total mass involved here is 2 times the mass of an electron, because if we've got an electron along with the positron which have the same mass. So 2 times 9.11 into 10 raised to the power minus 31 kilograms into c squared, which is the speed of light, squared. So E is equals to mc squared. The mass is 2 times 9.11 into 10 to the power minus 31. The total energy released is 1.64 into 10 to the power minus 13 joules. Part 2 says, calculate the wavelength of each gamma photon release. Now this energy, the total energy, is divided equally in the 2 photons that are being released, the 2 gamma photons. So each photon has an energy of 1.64 into 10 to the power minus 13 divided by 2, which is equals to 8.2 into 10 raised to the power minus 12 joules. Now we can use this along with the equation E is equals to hc over lambda to get the energy, to get the wavelength. The energy is 8.2 into 10 raised to the power minus 12. H is our Planck constant, 6.63 into 10 raised to the power minus 34. C is the speed of light divided by the wavelength. We'll make lambda the subject of our equation. We'll rearrange, and that gives us the wavelength equal to 2.43 into 10 raised to the power minus 12 meters. Part D says, explain how the gamma photons are used to produce an image. Now, we talked about these gamma photons that are being released. Now, to conserve momentum, because momentum is always conserved, the 2 gamma photons travel in exactly opposite direction. So that is the first point. 2 gamma photons travel in opposite direction. And these gamma photons are detected by the detectors outside. By outside, I mean outside the body. There's a ring of detectors around the body. The time taken for the gamma photons to reach the detectors is different depending on how far each gamma, the point where the annihilation process occurs is from the ring. The 2 gamma photons will arrive to the detector ring at different times, and that difference in time can be used to locate the point where the annihilation took place. This helps determine the location of production of gamma photon or the annihilation that caused this production. And this gives us the image of the tracer concentration in the tissue. So basically, depending on the amount of tracer that is absorbed by a particular tissue, we'll get a different amount of gamma photons produced, and that is used to create a final image. Question 12 part A says, state what is meant by the luminosity of a star. The luminosity of a star is the total power of radiation emitted by the star, or the total power output of radiation by the star. The luminosity of the sun is 3.83 into 10 to the power 26 watts. The distance between the earth and the sun is 1.51 into 10 raised to the power 11 meters. Calculate the radiant flux intensity F of the sun at the earth. Give a unit with your answer. So to find out the radiant flux intensity F, we'll use the formula F is equals to L over 4 pi d squared, where L is the luminosity, which is equals to 3.83 into 10 to the power 26. 4 pi d is the distance, 1.51 into 10 raised to the power 11 squared. The radiant flux intensity is equal to 1340. The unit would be watts for luminosity and d squared, hence meter squared. So watts per meter squared. Part C says, use data from B to calculate the mass that is converted into energy every second in the sun. The formula E is equals to mc. That is the formula that gives us the energy produced from mass, or the mass that produces a particular energy. So m is equals to E over c squared. The energy produced, we've got the power, which is 3.83 into 10 to the power 26 watts. So power is energy produced per second. And they're asking us for the energy in 1 second. So they're basically talking about power. So 3.83 into 10 to the power 26 over c squared. And that gives us the mass, which is equals to 4.26 into 10 raised to the power 9 kilograms. Part D says the radius of the sun is 6.96 into 10 raised to the power 8 meters. Show that the temperature T of the sun is 5770 Kelvin. So we'll be using the Stephen-Boltzmann's law that basically tells us that the luminosity of a star depends on its radius and its temperature, and the equation is L is equals to 4 pi sigma r squared t to the power 4, where sigma is a constant. So the luminosity of our sun, as given in the question, is 3.83 to 10 raised to the power 26. 4 pi. The constant sigma has a value 5.67 into 10 raised to the power minus 8 times r squared, which is the radius, 6.96 into 10 to the power 8 squared, times temperature T to the raised to the power 4. We'll make T the subject of our equation and solve for T. This would give us T is equals to 5770 Kelvin. Body of the question says the wavelength lambda max of light for which the maximum rate of emission occurs from the sun is 5 into 10 to the power minus 7 meters. The temperature of the surface of the star Sirius is 9940 kelvins. Use information from D to determine the wavelength of light for which the maximum rate of emission occurs for Sirius. We'll be using Wien's displacement law. for this part, and that says that lambda max, the maximum wavelength, is inversely proportional to the temperature. So for the sun, the maximum wavelength is 5 into 10 to the power minus 7, and the temperature is 5770. For Sirius, it's lambda, and the temperature is 9940. We'll cross multiply and solve for lambda. Lambda is equals to 5 into 10 to the power minus 7 into 5770 upon 9940. The answer that we get is 2.9 into 10 raised to the power minus 7 meters.